I want to give a perspective of what's happening in digital innovation from the perspective of the network. Lots of what we're talking about, what will be possible over the next 5-10 years, we are going to be transforming the underlying network infrastructure, the technologies that are used by service providers, by enterprises globally, to create an environment where we can conceivably automate everything. We can measure everything, we can control everything, and we can measure things at a scale and also at a time scale that is possible to create incredible levels of automation. This is already happening. We're beginning to see some of these elements being applied and adopted in enterprises globally, and it will begin to ripple out to the masses over the next, say, 5 years or so. Some of what I'll be talking about is part of our book, The Future X Network, that Bell Labs wrote about 2 years ago to understand and describe some of the underlying technological advances and also market advances that are creating a time of significant disruption across all industries. So technological revolution has two key ingredients. One key ingredient is a fundamental interconnection of systems and technologies and the capacity to profoundly transform society. So if you go throughout time, there's been a number of waves of technical revolution that have rippled through. Back in the 1600s, the financial revolution, where we took stocks and bonds as the enabling technology, and that together with the network effects created by banking systems created a tremendous financial revolution, banking and stock market infrastructure. First industrial revolution, we took the steam engine and iron production, that together with network effects of rail and shipping networks fundamentally transformed our economies and our society. Steel and chemicals in the second industrial revolution, combined with transportation networks, electricity, and telecom networks, created another technological revolution. We've been living through the information revolution, the basic enabling technologies, cloud, web, connected devices. That combined with the internet and broadband access has created tools and systems that have fundamentally transformed our societies. We're now at the beginning of what we call the automation of everything era, a time when now, thanks to all of this pervasive infrastructure that we have, as well as some new technologies we are deploying over the next 5 years, will allow us to measure and control everything, whether that be devices, things. Those are basic building blocks of controlling systems, as well as tremendous waves of innovation in data analysis, machine learning. Those components, the ability to connect and speak and talk to every device and machine and person in the world, connected with this ability to collect data and process that data in the digital realm to optimize things, and that connected to a new network that will allow this tremendous amount of scale, and also what I'm going to talk about is extremely low latencies so that we can control things very fast and at scale, is something we call the Future X Network. You look throughout time, we've had a tremendous growth in traffic since the early 1990s. How many people know Mosaic? I'm going to date. Yeah, that was my first internet browser. It wasn't much of an experience. It was kind of a automated card catalog back in the day. So you had curated content and you could find it. But it was great. And then came along Google. This whole era, we've digitized and delivered and shared information from the days of early sharing and early commerce with eBay and BitTorrent and iTunes to the era of self-generated user content, Twitter, video distribution. Throughout this entire wave, a lot of this wave has been driven primarily by individuals, connecting people, connecting things, getting access to content, the sharing of information. This growth will continue over the next decade. But what is really transformative is now we are at the point where we are going to be connecting everything, connecting devices, people, machines. That will more than double the amount of traffic, and it is this big step that we see causing a fundamental transformation in the way we build networks and the types of technologies that we use to build these infrastructures. This next wave is going to be driven not so much by consumers, but by enterprises and vertical markets. So far, a lot of what we've seen in terms of growth has been user-generated content. This next wave, I've been doing a lot of work with some early industries that are beginning to automate and use wireless communications technologies to automate their entire business process. We're seeing a world now where it was at a mining company a couple weeks ago that is an open pit mine, collects ore. Basically, their business model is blow things up and ship it to China. And this entire business process is very well understood. You can measure and monitor. They are automating the trucks that carry the ore from the bottom of the pit out to the crushers. They're automating the rail lines. They are instrumenting absolutely everything and controlling everything from a control center 1,700 kilometers away. All this is possible by the connection technologies and also the measurement and also the analysis that you can do to figure out what's the best way and the cheapest way to get that ore from the bottom of the pit out to ships and out to port. This new wave will be driven primarily by enterprises and verticals. We'll see new service providers building new types of networks for these types of infrastructures. And we'll also begin to see enterprises that are beginning to build their own private networks in order to serve these needs. And one of the big transformations we're seeing is driven by simple physics, latency, the amount of time it takes to transmit information from one point to another. We've lived in this world of IM chat, web loads, voice over IP, video conferencing, video streaming. In this world, humans are pretty tolerant of long delays. So in this world, where typically if you click a button for a website and you get something in 100 milliseconds, 200 milliseconds, that's fine. In this world, we've been able to build very centralized networks. So in the world of Google or Facebook, you build a data center somewhere where power is cheap and where you've got lots of connectivity. And it can be far, far away from the actual consumer or generator of that content. So here I've got a little plot of the amount of time it takes for information to flow from one point to another as a function of distance. So in this world where we've had, say, hundreds of milliseconds or more, even seconds, we've been able to keep the data centers about 1,000 kilometers away from where content was being generated. And this has really influenced the way we've built networks. We've been able to build networks where we put all the compute in data centers far away. We provide as much broadband capacity and throughput to those users to connect them to those data centers, and commerce continues. In this new world of industrial automation, we now need to really worry about delays. So what's happening? In wireless networks, we're beginning to take a lot of the control that we used to do in hardware, and now we're doing it in software. So we're actually building small data centers that actually create and do all the processing for 4G communications and 5G communications. In order to do that, we actually have to keep the data centers really, really close to the base stations. So we're already beginning to deploy networks that are operating at, say, 4 millisecond intervals. That means the data centers that we're building now are being brought within the order of 100 kilometers from the user, from the wireless device. But there's a whole host of additional applications now that require this extremely low latency. Virtual reality is one of the primary drivers for this new service on the consumer side and also on the enterprise side. And there's a human reflex known as the vestibulo-ocular reflex. It's something wired in our brainstem. If you quickly move your head to the left or your right, your brainstem detects that motion and moves your eyes in the opposite direction so that you can maintain focus on that saber-toothed tiger. Now, if you move your head to the left or right and your field of view does not keep up at that very, very low delay, you end up getting seasick. And this is one of the reasons why some of the early virtual reality experiences people reported playing games and feeling really, really nauseous. It's because the networks and the computers weren't able to process the image fast enough to keep up with head movements. So in this new world, if we want to do any type of virtual reality, we're going to have to build networks that are capable of very, very low latencies. That means we have to bring the data centers within 100 kilometers of the actual usage. There's also other applications, cloud-assisted driving, autonomous vehicles, electric grid control, We already see this happening in the high-frequency trading market, where real estate close to data centers that connect to Wall Street are very valuable. It makes sense to have that processing very, very close to the edge of the network. Virtual reality is also, in addition to the latency, generates tons and tons of data traffic. So if we want to be able to support virtual reality in a mobile environment, we need now wireless technologies that are capable of not only supporting these extremely low latencies, but extremely high bandwidths. So virtual reality typically generates about half a gigabit per second of traffic. That's far beyond what we can do today with today's wide area wireless technologies. So we need to do something different in order to make these services work. So here's a high-level view of some of the new services and old services that we have been using in the world. So the world of home sensors, chatbots, streaming video, also 360-degree high-res video. We can live in a world where we're pretty far away. We can centralize things pretty far away from the user. Delay isn't so important. Also very, very high data rates. In this new world of system control and virtual reality, the delays are much, much smaller, but also the throughputs are really, really high. So in order to build networks like this, we have to move the data centers very, very close to the user. And we also need to deploy new types of technologies to provide this kind of connectivity. So today, we've got Amazon, Google with their core cloud infrastructure. This is where all their racks of servers are. They have international scale IP networks that are connecting all this infrastructure. And then they're using local service providers to provide this type of broadband access. In this type of world we've been living in up until now, we are providing services about 10 megabits per second. The delays that we're designing for is about 100 milliseconds. We've had about 10 billion devices or so. And the devices have been fairly expensive, say $1,000 for the new iPhone 7. I'm losing track of what number we're up to now. And battery life typically of about a day. In this new world where we're connecting things and machines and devices, we need to support much, much higher data rates, say 10 gigabit per second. We also have to bring the latency really down, a millisecond. We need to also support many, many more devices because we're connecting things. And if we want to connect things in a way that we don't have to think about it, it becomes a no-brainer to add a wireless device to anything that you ship from a factory or any device, any object. We need to drive the price of these devices down to on the order of $1 per device. And we also need to bring the battery lives of this technology from one day, where we are today, to 10 years. So in this hyper-connected world where we're connecting everything, we're providing digital interfaces to everything, we want to use that for business processes, we want to use it to optimize the world. In this world, we have to fundamentally change the way we build networks and also design new technologies to satisfy these extreme requirements. So we're moving to a world that is no longer centralized, but highly distributed. So IP networks are going to interconnect everything. Our compute technology that we use for decision making and for control is going to be scattered throughout the globe, and we will be assigning those data centers based on the real-time requirements of the applications. We need extreme broadband access in order to access things, and we need new technologies to be able to hit these high data rates and very low price points and long battery lives of the devices themselves. So 5G technology. How many people have heard of 5G? Who's heard of 6G? No, not quite yet, but we're getting there. So 5G technology is being developed right now and tested. And it's designed to be a wireless technology that satisfies all of these requirements simultaneously. Extremely high data rates, so in excess of gigabits per second. Extremely low latencies, so that we can control things at scale and also control things very, very fast. Also provide extremely low-cost devices. This is something we call ultra-narrowband. So a lot of these new technologies, in order to get these very, very high data rates, we have to use lots and lots of spectrum, lots of new spectrum. You will have heard something of millimeter wave spectrum, of spectrum that is very, very, there's lots of it available, but because it's in such high frequency bands, it doesn't transmit very far, so we have to bring base stations very close to the users. In addition to these wideband technologies, in order to make very low-cost devices, we are endowing this technology with the ability to use very, very small slivers of that spectrum. And when we use very, very small slivers of that spectrum, we can design devices that are extremely cheap and also use extremely small amounts of power to transmit. When we take that ultra narrowband technology and combine it with all sorts of power management technologies in the network, we can build technologies that now are possible to support 10-year battery lives. And we're also building this to support extremely low latencies, 1 millisecond scale latencies. That will allow us to provide extremely tight control for all of these new industrial applications. So if you look at any kind of high-level view of industrial automation, first you need to put sensors out in the world to be able to create a digital view of the analog world. So the ability to create a digital nervous system, which is sensors that we can place anywhere because it's a wireless technology. And the only limitations we have on the sensor technology are the device physics themselves, chemistry, materials, speed of light. Over the next 5-10 years, we will continue to have incredible innovations in this whole sensor area. We also need to be able to anticipate and control things. And this is an area we've seen tremendous innovation over the last 5 years, machine learning, techniques where we have out in the cloud access to tons and tons of data. We also have access to tons and tons of compute power. And in this world, we are able, since we can now make accurate digital models of the physical world, we can use those digital models now to control, optimize, and speed things up. In a lot of industrial applications, we also need to be able to give humans the ability to act at a distance. So in very hazardous environments, such as this mining example I was talking about, you want to be able to endow remote operators with virtual reality glasses, have them control robots from hundreds of kilometers away, so that when they go and blow up the earth for a mining operation, the people are not in harm's way. So that's going to require very high data rates and very low latencies. And also, you need to be able to actuate at a distance. So to be able to control drones, move things around. These are the 4 basic building blocks of any industrial automation system. And the key to supporting this is to have a very high-speed, low-latency network. With a wireless network that is extremely low latency and also high bandwidth, now I can instrument everything, I can control everything, and now I can also take advantage of a lot of the innovations that are happening in other parts of the industry. Low latency really matters in these industrial automation examples. And one of the reasons is when things are moving, you need to be able to tell them to do something. In an extreme case, you need to tell them to stop. And if you look at typical speeds that you see for example, a robotic control or a drone application or an automated vehicle, the amount of distance you travel within a certain length of time impacts safety as well as how tightly you can control the system. So a robot arm moving about 3 meters per second, this is the time scales that we're operating under today's wireless technologies. So in an industrial floor application, 3 meters per second, if you say stop, it can take 100 milliseconds for that stop command to get to the robot. 30 centimeters has gone by. And in many industrial applications, that's a lot of distance. Drones, similarly, 3 meters, 10 yards within today's technology. A car moving at 150 kilometers per hour, stopping, if you send a command to stop the car, that's roughly half a car length or more in this old technology. The technologies that we're doing right now, this 5G technologies, will allow us to control at much finer levels of granularity and scale, and which will enable a whole bunch of new applications. Another thing from control theory, So when you're trying to control things, delay is bad. And the more delay you have, the less able you are to control things. So when delay is extremely high, there's no way possible to make a system stable. So there's no way to control it remotely. When you have very low delays, if you command the robot to go somewhere, it can happen very, very fast. So low delays allow you to create very large-scale, very hyper-reactive systems. This has a lot of applications across the industry, including platooning and remote vehicles. We expect that vehicle technology will continue to use a lot of local processing, a lot of local AI techniques to control devices. But there's always a benefit in connecting those devices with a network, because there are things that your car does not see that other cars ahead of you may see, or there may be information that the network knows about driving conditions that can help you be safer and help control the systems better. So being able to take a platoon of vehicles and control them down to a millisecond latency will allow you greater safety and allow you better efficiency through these systems as well. We're already seeing a lot of work in industrial automation. So today, this is largely done using wired technologies. So if you want to put together a bunch of machines in an industrial control environment, there's typically using fiber to interconnect all these machines. When you use fiber, you lose a lot of flexibility in the systems themselves. You'd like to be able to move the robots to the work. You'd like to be able to remotely and automatically configure a shop floor. Bringing this hyper accuracy and very low latency technologies down to the shop floor will open up a whole body of new use cases as well. Being able to optimize and know position, we talked about it in the outdoor environments. Similar things happen in indoor environments. We need new technologies to be able to do that don't involve satellite reception. So already we're seeing industrial robotics. This is an area of a lot of innovation. Also, a lot of new standards are being developed so that we can provide wireless connectivity for tomorrow's robots, interconnecting cars. Lots of interesting work going on in outdoor 3D printing of buildings using large machines that use injection molding and use cement to create novel structures. To be able to cooperatively control swarms and herds of robots, there's a certain amount of that will always be done by the robot itself, but that is always enhanced and made better with greater coordination. Cooperative drone control and also teleoperation. So we're in the middle of this big shift right now. 5G technology that we're building is designed to support a lot of these technologies and a lot of these use cases. We're also, because we're moving into a world where we have now hyperscale. We have many, many more devices to manage, many, many more networks to manage, many, many more data centers to manage. We have to do a lot of things in the development of the underlying network technology to make all of this happen. So we're developing a lot of automated technologies, automation technologies to use in the network to be able to optimize the network itself, to be able to respond to failures in the network, to be able to apply AI techniques so that machines themselves can manage the networks so that we can bring the cost down and the reliability high. Just a number of areas that we're working at in Bell Labs. So in order to make this world happen, we have to be able to connect things at very, very high speeds, no matter what type of connection we have, whether that be wireless, wireline, fiber, twisted pair. Lots of technologies in multi-input, multi-output antennas, very, very large-scale antennas that are small, low-cost, that can create this reliable, high-bandwidth connection. Being able to move clouds and control clouds in real time, something called edge clouds, in order to enable these very, very low-latency applications. Network fabrics that are able to dynamically respond to changes in environment and failures. The ability to do a lot more things in software than we had done in the past to keep flexibility for different types of applications. Being able to automate the operations of a network, bring AI into the control of these networks, as well as overarching digital data security to make sure that all of this interconnection happens with trust and privacy. Just to touch on a couple of things that we're doing in the labs to make this happen. So we're envisioning a world where a lot of these devices are going to be small, and low power, and body worn. And in order to enable a whole area of analytics, we have to take the compute power that today is out in the network and somehow do this on very low form factor devices, very low power devices, devices that don't have a lot of memory, don't have a lot of compute power. So we're doing a lot of work to make that happen on small scale devices, as well as develop new sensors, body-worn sensors, skin contact sensors that are capable of instrumenting and digitizing the human body measurements. Being able to automatically control and respond to changes in the network. Here we have a picture of a proof of concept we did. This is a completely wireless small cell. This is a small cell that a drone can send out into the field if it notices there's a concentration of people or devices with heavy traffic. The cell can be deposited. It opens up. It's got solar panels, so it doesn't need power, and also has a wireless backhaul connectivity to the network. And it automatically sets itself up. We're also working in the realm of intelligent processing, so building more and more scalable processing platforms that can process these massive amounts of data from all of these devices, increasing the capacity of undersea cables, new ways of grabbing intelligence from data, as well as automating systems. Lots of work also in the area of these massive high data rate small cells. So here's a picture of a prototype small cell with many, many antennas on it that's capable of getting these high data rates, gigabit and higher, using copper and other medium to get extremely high data rates. Sensors for the skin. Lots of work in virtual reality, as this is a fundamental building block of entertainment as well as industrial operations, and also ways of moving data, moving video, and storing video in ways that are highly efficient. So this is just a touch of some of the things that we're working on. This new world will create lots of disruption in the service provider market. So we expect to see probably a lot more consolidation, some more global players in the network space to be able to create this international connectivity. But because of this low latency services, there's also an opportunity for local companies, because they're advantaged by being close to the customer. They have data centers that are close to the customer. They have fiber that's close to the customer. They'll also create a new market dynamic in this world as well. And also a move to a lot of private networks that are deployed by enterprises themselves to control their operations dynamically. So with that, thank you very much for your time.